Hello, this is Jude Socrates, and welcome to A Portrait of Linear Algebra. Our video for today is about finding the inverse of a matrix. So you will be happy to know that unlike our last video, which had so much theory and just a little bit of computation, it's going to be a little bit more balanced this time. There will of course be some theory, but there will also be a lot of computation. So in our video for today, we will first learn about the 2-for-1 theorem for the matrix inverse and bijectivity, which actually gives us a very significant improvement on how to find the inverse of a bijective operator or a matrix. We will see the connection between elementary matrices and invertible matrices, and we will see how to test if a matrix is invertible or not, and incorporate that test into the algorithm that we will learn that will find the inverse of a matrix for us using, surprise, elementary row operations. So it's going to be a lot like solving a system of linear equations, as we are going to see very soon. So here is the 2-for-1 theorem for the matrix inverse, which, as the name implies, gives us 50% less work to do when we're finding the inverse of a matrix. So here it goes. Suppose that A and B are n by n matrices. Then A and B are invertible and they are inverses of each other. In other words, A inverse equals B and B inverse equals A if and only if A times B is the identity or B times A is the identity. And you might be thinking, isn't that the definition of an invertible matrix? And you are almost right. The forward direction of this if and only if statement is obvious. If A and B are invertible and they are inverses of each other, then that definition says that A times B and B times A are both the identity. And in fact, of course, that's true. A times B is A inverse, which is identity. B times A is also A inverse A, which is, again, the identity. So it is, of course, the backwards condition or the backwards implication, which needs some proof. So for the converse, we are only given that one of the equations is true. Let's say it is A times B equals the identity. And of course, a similar argument will hold for the opposite equation. B times A is the identity. For this direction, we are going to recall the theorem at the end of section 3.5, which we said is going to be useful in the homework in the next section. And here we are. What did it say? It talks about the one-to-one and onto properties of a composition. Suppose that T1 is a transformation from Rn to Rk, and T2 is a transformation from Rk to Rm. So that means that we can form the composition T2 composed T1 as usual. The codomain of T1 is Rk, which is the domain of T2. So T2 composed T1 is well defined. What are the conclusions for this theorem? If the composition is one-to-one, then the inner transformation, or the first transformation, another way of thinking about it, has to be one-to-one. But also, if the composition is onto, then the second or the outer transformation this time has to be onto. Okay, so why is this theorem important? Well, we have this equation. We are given that A times B is the identity in the converse direction, let's say. So these two matrices correspond to two operators, T2 and T1. So let's have T2 correspond to A and T1 correspond to B, so that A times B is the same as the matrix of T2 times the matrix of T1. But when we talked about compositions, we said that the matrix of the composition, T2 composed T1, is the product of these two matrices in that order. Okay, so now what do we have? The matrix of T2 composed T1 is the identity. Well, if that composition has matrix identity, then the operator corresponding to that composition has to be the identity operator on Rn by the uniqueness of the matrix of a linear transformation. But since the identity operator is both one-to-one and onto, then we can conclude that the inner transformation T1 has to be one-to-one and the outer transformation T2 has to be onto. Okay, so that is where we are. However, now we have the dimension theorem. The dimension theorem says, I hope you remember, that the rank plus the nullity of a matrix is the number of columns. We have an n by n matrix, so we have n. Even if you forgot that it was the number of columns, it would still be n because we have a square matrix. So what do we have here? If T1 is one-to-one, the nullity of T1 is 0, therefore the rank is n. Okay, so that means that aside from being one-to-one, T1 is also on 2. Now how about T2? Well, it's the same idea. If T2 is on 2, then its rank has to be n. So therefore its nullity has to be 0. So therefore T2 is also one-to-one. So where are we? Both T1 and T2 are one-to-one as well as on 2. All right, so there we are. Since T1 and T2 are both one-to-one and onto, A and B are both invertible. So we have an A inverse and we have a B inverse. Okay, but wait a minute. We are told that A times B is the identity. Okay, so what happens if we multiply both sides by, let's say, A inverse? So we get A inverse times the identity has to be A inverse times the matrix product AB. But we have the associative property, so we can rewrite the right side as A inverse times A times B on the outside. But wait a minute, A inverse times A is just identity. Multiplied by B, we get B. Oh, so therefore B equals A inverse identity. Oh, but wait a minute, that left side also simplifies, and it simplifies to A inverse. Okay, so we get that B is A inverse. So we get that if you reverse the order, we will get B is A inverse. So A inverse A down there. And again, we get the identity. So there you go. We have both equations. If A times B is the identity, then B times A is also the identity. And of course, an identical argument applies if you have B times A is the identity. So as a bonus, we get another theorem. You can never have too many theorems. Notice that we showed that if the nullity is 0, then the rank had to be n. And if the rank were n, then the nullity had to be 0 for a square matrix. So that shows that if T is an operator, goes from Rn to Rn, then T is one-to-one if and only if T is onto. So in other words, T is bijective if and only if either T is injective or T is surjective. And again, if you were remembering, isn't the definition of bijective that it is both injective and surjective? And of course, you would be correct. But we just showed that if it's already injective, nullity is 0, so rank is n, which means it's also surjective, and vice versa. Oh look, numbers! Finally, we get to some computations. Not too bad. It's only 10 minutes into the video. So, on our way to finding a method to compute the inverse of a matrix, let's think about elementary row operations. So we said that if you take the identity matrix and then perform a single elementary row operation, you get what's called an elementary matrix. So what does this theorem say? If you have an elementary n by m matrix and A is any n by m matrix. So this time we're writing it kind of backwards, okay? And that's because we are going to write the matrix product E times A in that order, okay? So the number of columns of E has to be the number of rows of A. But A can have as many columns as you want it to have. So this theorem says that the matrix product E times A can be computed by performing the same elementary row operation on A that was used to produce E from the identity. Okay? So we have this example over here. A is a 3 by 4 matrix. So we will multiply A to the left by one of these elementary matrices. Okay. So I put them in the order type 1, type 2, type 3. So remember, type 1 is a scaling operator. So we multiply, in this case, the second row of the identity by negative 3/4. So we scaled row 2. Type 2 is a switching operator. So we switched row 1 and row 3. Row 2 stayed where it's supposed to be. I decided to use the same number, negative 3/4, in both the scaling transformation and the sum transformation. So to get the third row from the identity matrix, we take the second row of the identity matrix, multiply it by negative 3/4, and add it to the third row. So we don't change the second row. We temporarily compute negative 3/4 times the second row, and then we add it to the third row. Okay? So all of these three are elementary matrices. I've gone ahead and made copies of these three matrices on the left, and I copied A on the right. Okay, we are going to perform these three products. Now, before I click, let's think about it. Let's use the dot product version for matrix multiplication. Think of row 1. What happens when you multiply row 1 to the matrix A? Okay, so think about row 1 and you take the dot products with column 1, column 2, 3, 4. These are zeros, so therefore 4 and 2 will not contribute at all, meaning the second and third rows will not contribute at all. The 1 gets multiplied to the 9, and then the 7, and then the -2, and then the 3. So the first row doesn't change. Okay, let's go down to the third row. This time you have 0, 0, 1. So when you take the dot products, 9 and 4 will not contribute. The 1 will get multiplied to the 2. Column 2, 7 and -12 won't contribute. You'll get the -3. So the third row does not change when we get the product. Let's go to the second row. So we have 0 minus 3/4, 0. So again, those zeros. 0 will annihilate the 9. That 0 will annihilate the 2. So the first and the third rows don't contribute. What's going to happen? We will multiply the -3/4 to the 4. We're going to get -3. We're going to multiply -3/4 to the -12. We're going to get 9. multiply 8 to minus 3/4, you'll get minus 6. 0 does not change. So what's going to happen? We are going to take the second row and multiply every number by minus 3/4. And that's what's going to appear in the matrix product. There it is. -3, +9, -6. The first and the third rows don't change. Okay, so hopefully we learned something from those zeros and ones, because here they are again. Row 1. This time you have 0, 0, 1. So when you multiply that to each column, these two zeros will annihilate row 1 and 2, but that 1 will get multiplied to 2, and then -3, and then 6, and then 6. So row 3 will now be found in row 1. What about 0, 1, 0? So this time, the 9 and the 2 will disappear, and the 1 gets multiplied to the 4, and then the -12, the 8, 0. So row 2 does not change. Last row, 1, 0, 0. So 1 gets multiplied to 9. Zeros will kill the second and the third row entries. So we're going to get the 9, the 7, the -2, and the 3, but this time they will appear in the third row. So what happened? We switch the first and the third row. Second row stays where it is. Boom. Okay. Last type. So we will add a multiple of the second row to the third row. Okay. Ones and zeros. Row 1 doesn't change. 1 times 9, 1 times 7, and so on. Row 2, 0, 4, 0. 0 minus 12, 0. Row 2 does not change. What about row 3? Okay, so this one, it's always type 3. That's most complicated. 0. Nothing's going to contribute from row 1. -3/4. So you multiply 4 by -3/4. That's where we got the -3. Okay? But now there is still a 1 there, so you will add 2. -3 plus 2, we should get -1. Column 2, 7 doesn't contribute. -3/4 times -12, the plus 9. But we still have the 1 times -3, so we will get 9 minus 3, 6. So what's happening? We're multiplying every number in the second row by -3/4, and we're adding them to the corresponding entry in the third row. But that's exactly how we got this matrix from the identity. Add -3/4 of the second row to the third row. So what should we get? Based on these numbers, we should get -1, 6, 0, 6. Is that what we get? Yeah, -1, 6, 0, 6. So based on that idea, we are now going to actually compute inverses of elementary matrices, and they are 3 by 3. So in our last video, we could only invert 2 by 2 matrices. So these are now the first 3 by 3 matrices that we will invert. And of course, because of all the zeros and ones, it's going to be easy. Oh, elementary. Okay, so this theorem says that elementary matrices are invertible, and the inverse of an elementary matrix is another elementary matrix, and it is of the same type. So the inverse of a scale also has to be a scale. Inverse of a switch has to be a switch. Inverse of a sum has to be a sum. All right, so here are the 3 elementary matrices. We're going to look for their inverses. This is where the 2-for-1 theorem is going to be very useful. So it said, if you have a candidate for a matrix inverse, B, in order to be the actual inverse, all you have to check is that when you multiply A by B or B by A, you get the identity. If so, that matrix B has to be the inverse of A, and A has to be the inverse of B. So, what's the idea? If you multiply any matrix to the right of an elementary matrix, what you would get as your answer is what you would have gotten if you had performed that same elementary row operation on the matrix on the right. So many words there. So let's start with, how about let's just put the identity matrix on the right. Okay, so there you go. Of course, if you multiply those together, you will get the same matrix on the left. We know that. It's just written a little bit differently because of Maple. Okay, but what's the point I want to make here? You get the answer by multiplying the second row of the identity matrix by -3/4. The first and the third rows don't change. So how are we going to get, instead of -3/4, 1, positive 1? So what does that mean? I need to think of a number in that position so that when you multiply that number by -3/4, you get positive 1. Well, you know algebra. Oh, linear algebra. We are looking for -4/3. If you multiply those two numbers together, you will get positive 1. So is this an elementary matrix? Yes. Is it also a scale? Yes. But notice, if this is C, C is not 0. This is 1 over C. It's the reciprocal. Okay. Type 2, switch. So let's piggyback on that idea, right? We said, if this were the identity, then what will we do? We will switch row 1 and row 3. So of course, if you multiply these together, you'll get that same matrix. But we don't want that matrix. We want to get as our answer the identity. Okay? So therefore, what has to be in this matrix? Well, row 2 is already in the correct position. This will take row 3 of whatever matrix is here and bring it up to row 1. Oh, so this has to be in the bottom. Okay. Similarly, this 1 over here will take whatever is in row 1 and put it to the bottom. So this bottom row had to come from row 1. Is that going to work? Boom. So yes, this is the matrix, inverse matrix of the, oh, wait a minute. They're the same matrix. Oh, and that makes perfect sense, okay? Because when you switch, and then you switch again, then you're back where you started. Okay. Last one. Again, always the most complicated one. Okay. We are looking for a matrix, another elementary matrix, and hopefully it's type 3, so that when you multiply it to the matrix on the left, you will get the identity matrix. Okay, that's the equation we want. Okay, so again, row 1 and row 2 will not change. So they're already correct. What about row 3? Well, this third row will take -3/4 of whatever is here and add it to whatever is here. Okay, so if I want to get 0 for an answer, and I'm going to keep that -3/4, that 1 rather, because I need it for row 2. then what has to happen? That minus 3/4 has to cancel with whatever is down here when you add them together. So it's not minus 4/3, it's going to be positive 3/4. Okay, so the negative 3/4 turns into positive 3/4 in the inverse. Is that the correct guess? Yes. Okay, so please do not confuse these two operations with each other. Okay, if you have a scale operation, you have another scale operation if you have the reciprocal here. If you have a sum operation, you have another sum operation, but you have the additive inverse this time. It's the negative. What does the 2-for-1 theorem say? If this second matrix does exactly what it's supposed to do when you multiply with the first matrix, then you have found the inverse of that matrix. Okay, so elementary matrices are, of course, very easy to invert. Yeah, that's another good reason why they're called elementary. So what do we need for more complicated matrices? Well, first, here's a preliminary test for invertibility. Actually, you already know this. Suppose that A is an n by n matrix. Then A is invertible if and only if the REF of A is the identity. So that's not difficult because the definition said if you want a matrix to be invertible, then the operator that it corresponds to has to be both 1-to-1 and onto. But how do you tell if an operator is 1-to-1 or onto or both? You look at the REF. To be 1-to-1, you can't have a free variable. So the nullity is 0. The rank is also n. To be onto, the rank has to be n. Oh, we already said that. We already had that from the 1-to-1 property. Okay, so it can't have a free variable. It can't have a row of zeros. So what is its REF? It has to be the identity. Because if it's not the identity, then you have not enough leading ones. So you have a row of zeros, and you also have a free variable. All right, so we are going to combine that in the algorithm that we will need to actually compute the inverse of A. So here's the algorithm. And if you took college algebra, you might have seen it already. Now we find out, why does it work? Suppose that you have an n by n matrix. Let's construct the n by 2n augmented matrix. So it's going to be really wide. You put A on the left and you put the identity on the right. So that's why you double the width of that matrix. Then A is invertible if and only if the REF of this augmented matrix contains the identity in the first n columns. So we said that a minute ago. Because A is on the left side, to be invertible, the REF has to be the identity. So therefore, in this augmented matrix, we will see the identity in the first n columns, the left side of this double wide augmented matrix. If this is what you got, then miraculously, A inverse will be found in the last n columns of the REF, the second half, the right half of the REF. So in other words, the REF of A augmented by the identity is the identity augmented by A inverse. Okay, so why does this work? You're not in college algebra anymore. You're in linear algebra. So we want to know why things work. Okay, so we start with the augmented matrix. Okay, and I put that over here. And then we do Gauss-Jordan. No, not quite. We do row operations. So again, you don't have to divide the first row but by whatever first non-zero number you see there. That will give you fractions. We don't want fractions right away, do we? So you do row operations. Maybe you will add a multiple of one row to another row. Here's an example. Suppose we're going to invert this. And yeah, that's what we're going to do in a minute. How do we get a leading 1 up here instead of a 3? Divide everything by 3. No, don't do that. How about if we just subtract row 2 from row 1? Isn't that easier? Then we'll get 1 minus 9 plus 11. Okay, so we're going to do that. We're going to probably do 10 or 11 or 12 elementary row operations. You'll get that leading 1. Then you'll clean up column 1. You'll make these zeros. And then you need a 1 here. That's not going to stay 1 for very long, probably. And then you want 0 down here, and then a 1 here, and then you make zeros here, and then you make zeros there. Okay? I hope you remember your solving, how to solve a system of linear equations. Okay, so what does that mean? We will perform a row operation, and then another operation, and then a third operation, and so on. But remember, our second theorem, I think, said that performing an elementary row operation is exactly the same as multiplying the matrix to the left by an elementary matrix. So that's why instead of writing subtract row 1 from row 2 or blah, 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 I have these elementary matrices. So you perform these matrix products until you get the REF, which on the left side will have the identity. On the right side, we don't know what it is. We're trying to show that that right side is B. Okay, but now, what did we say? Multiplying by E1 is the same as performing the row operation. Okay, but how would you multiply this matrix by E1? Well, we know how to do it column by column, right? Correct. So therefore, what we have on the left over here can be rewritten as, yes, I can put it over here. I can put the E1 inside the product. Okay, so E1 on the left part and also E1 on the right side. Okay, and then we keep going. So we will multiply E2 inside. Okay, but you know what? Before we do that, doesn't E1 times IN simplify to just E1, right? So now bring E2 inside. So we will get E2 times this product, and then E2 times that single matrix. And again, we have the associative property, so we don't have to bother with parentheses, right? Okay, so we have taken care of E2, taking care of business. All right, and then we keep going, we keep going, we keep going until we have multiplied every matrix into our augmented matrix. Okay, so that is gone. Okay, so now we have this huge augmented matrix equal to this augmented matrix. So let's copy that down here. That's our conclusion. So now, matching time. This matrix product has to be, what's on the right side? This guy. And this matrix product has to be, what's on the right? This guy. Wait a minute. This guy over here is the same as this guy over here. Ooh. So B times A is the identity. Looks familiar? Remember the 2-for-1 theorem. If B times A is the identity, B has to be A inverse, A has to be B inverse. But that's okay. We're looking for A inverse. So there you go. B has to be A inverse. And where is B? It's what you find on the right side of this augmented matrix. All right, so we are now finally able to do our example. We have this matrix. We want to find the inverse. So the easiest way to do that is to go compute matrices inverse. Just kidding. Of course, you don't have this fancy calculator. I do. Haha. So I'm showing you this because when you do your homework, once you finish the first part of finding the REF, in other words, you have gotten 100,101, your bottom row is now fixed. It's now done. So check the bottom row in the answer key. Okay, especially if your teacher is not allowing you to use an online matrix calculator. Check that your bottom row is correct. And then, once you fix the second row, check that the second row is also correct. And then hopefully the top row will be fine. Okay, so let's go to our online matrix calculator and we'll get this REF. Okay, so we're back to this website. So let's enter the matrix. We have 3, -8, 5, and then 2, 1, -6, and then -4, 0, 7. Okay, on the right side, we will put the identity matrix. So we have 1, 0, 0, 0, 1, 0, and then 0, 0, 1. Okay, submit. Okay, so here is the initial matrix. All right. So our goal is to get the REF. The identity should appear on the left, and whatever is on the right should be our inverse. Okay, so we said earlier, let's just subtract row 2 from row 1. So add -1 times the second row to the first row. Okay, so that's our second matrix. We are now ready to clear the 2 and the -4. So add -2 times the first row to the second row. Okay, so we now get 0 there. Now add 4 times the first row to the third row. Okay, so we got the zeros. Okay, now we want to turn second row into 0, 1, 0. Okay, in our answer we had a 39. Ooh, we have a 19 there. Okay, well, let's see now. Oh, here's an idea. We can make a smaller number. Okay, 19 times 2 is 38, which is not that far from 36. So let's add twice the second row to the third row. Ooh, there you go. So the third row now has a 2. Oh, wait. So now it's easy to change that 19. Haha. So let's see. We need 9 times -9 times row 3 to the second row. Right? -18 plus 19 gives us 1. There you go. No need for fractions yet. So now we will fix that 2. We will need -2 times the second row added to the third row. There we go. So now we have that 0. We are ready for the third row. Okay, now we have no choice but to divide the third row by -39. Okay, so we did see in the answer that there is a fraction all over the place. They're all fractions. So therefore, we will multiply the third row by -1 over 39. Okay, so that's now a scale. Do it. Okay, there we go. And of course, our bottom row is correct. We're now ready to clear the third column, 11 and the 17. So add negative 11 times the third row to the first row. There's our 0. These will not be correct just yet. Okay. For the second row, add negative 1 over 17 times the third row. I'm sorry, negative 17 times the third row. Oops, almost. To the second row. Yeah, there we go. The second row should now be correct. Minus 10, minus 41, minus 28. Excellent. So now, last step, clear that minus 9. So add 9 times the second row to the first row. Okay, so boom. And that is the inverse that we saw in our last screen. So this 3 by 3 matrix is our A inverse. All right, so that is our video for today. As usual, this is Jude Socrates signing off. Thank you so much for watching this video. You will find me on Facebook, and you will find the 4th edition on Facebook and at kindlehunt.com. So until our next linear algebra video, I hope you enjoy the rest of your day. Bye.